Um, Imagine for just a second that you were standing in your bathroom and you just stepped onto a scale.
Right, and you look down at the number.
Yeah, and maybe you sigh. Maybe it's not the exact number you wanted to see today.
We've all been there.
But before you get too frustrated with yourself or try to blame the physical stuff that you were made of, we actually have some incredible news for you based on the stack of research sitting in front of us today.
Really good news, actually.
You cannot blame your stuff because, technically speaking, 99% of your mass is nothing but empty space and trapped, frantic motion.
It's the ultimate cosmic optical illusion. Why things have weight at the most fundamental level.
Right.
And the core thesis we'll be exploring is that the universe isn't a collection of solid things at all. It is a collection of processes.
Processes. I love that framing.
Mass, as you experience it, is essentially a localized cosmic traffic jam. I mean, it is trapped energy.
A collection of processes. The research today is taking us really deep into the microscopic world, specifically into the realm of quantum chromodynamics.
Which is an incredibly beautiful, complex framework.
Yeah, one that we are going to tear apart and examine piece by piece. We're looking at the mechanics of force-carrying particles called gluons, the architecture of the strong nuclear force, and the fundamental creation of mass.
Welcome to the Deep Dive. I'm Satosha.
And I'm Satoshi.
It's a heavy topic.
Very heavy, no pun intended. But before we get into the heavy stuff, I think we need to address the particle in the room.
Oh, I know where you're going with this.
We need to talk about the massive public relations problem in modern physics.
Yeah. The God particle PR problem. You're talking about the Higgs boson.
Yes, and the pervasive myth that it is the sole creator of mass in the universe.
It really gets all the press, doesn't it?
Yeah, it gets the magazine covers, the Nobel Prizes, the high-budget documentaries. Whenever the topic of mass comes up, the narrative always centers on the Higgs field.
Acting as this invisible cosmic molasses that drags on particles.
Right, and gives everything in the universe its weight. But looking at the actual quantitative breakdown in the research today, it feels like we've all been sold a bit of a marketing gimmick, or at least a severely incomplete story.
It is an incredibly common misconception, even among science enthusiasts.
Yeah.
And it's one the research corrects right out of the gate.
So set the record straight for us.
Well, the Higgs boson and the Higgs field are undeniably vital for the fundamental blueprint of reality. They give fundamental particles like quarks and electrons what we call their bare mass.
We're baseline.
Exactly. They establish the baseline. But if you look at the actual mass budget of a human being, or a planet, or a star, that Higgs mechanism is responsible for a measly 1% of the mass in ordinary matter.
1%. That is a staggering discrepancy.
It really is.
If the Higgs field were completely turned off tomorrow, just zeroed out across the cosmos, the protons and neutrons making up your body would only lose a fraction of their weight.
The universe would look very weird, obviously.
Chemistry would be completely rewritten.
Right. But you would still have solid, heavy matter. The Higgs is basically just the cover charge to get into the universe. It doesn't account for the actual heavy lifting.
Which means the true origin of mass peril, the mechanics doing the other 99% of the work, is happening somewhere else entirely.
And that's what we're looking at today. We are giving the spotlight to the unsung heroes of the Standard Model.
We're looking at how the universe dynamically generates substance out of massless components.
So let's start the audit.
Real quick before we jump into the deep end, if you are getting value out of this show, we request you to check us out on Fountain FM. It's a value-for-value player where you actually get paid for listening without advertisements blocking your experience.
It's a great platform.
And of course, you can listen to us on Spotify, Apple Podcasts, or YouTube Music for free, or wherever you get your audio fix. As for videos, we still need to hit our goal of 1,000 subs on YouTube to start using the Mosaic AI video editor.
Mosaic is truly a game changer for small creative like us.
It really is. We can feed it a YouTube link, and it creates beautiful AI cinematic captions, infographics, and a whole lot more we're still discovering in our capability tests. We can't be more thankful that you all are as fascinated by these deep dives as we are.
The key to this vote of confidence is the research we share on our website.
Exactly. No login needed, no cookies, no trackers, and absolutely no advertisements. So please, if you want to dig deeper into the numbers, check the link in the descriptions.
Because today is a big one.
Huge. Let's unpack this.
If we want to understand mass, we have to look at the most ubiquitous, stable, heavy particle in the universe, which is the proton.
The anchor of the atomic nucleus.
Right. And classical physics operated on a very simple, logical assumption for centuries. The weight of a whole object should simply be the sum of its constituent parts.
Makes sense. If you have a bag of marbles, you weigh the bag, you weigh the marbles, and the math adds up perfectly.
Exactly. But the subatomic realm is inherently hostile to classical common sense.
As always.
When physicists run an audit on the proton, they find a massive accounting error. We know a proton is not a fundamental particle. It is a composite particle made up of three smaller entities called valence quarks.
Specifically, 2 up quarks and 1 down quark.
Correct. So, applying classical logic, we should just be able to measure the mass of those three quarks, add them together, and arrive at the total mass of the proton.
Right, the marble bag logic.
But when researchers measure the isolated bare mass of those three quarks, that's the mass imparted to them by their interaction with the Higgs field, it only accounts for roughly 1% of the proton's total observed mass.
That's the 1% we were just talking about.
Yes. To put numbers to it without getting bogged down in the equations, on the subatomic scale, we measure mass in electron volts. A proton sits at roughly 938 units of mass.
Wow.
But the three quarks themselves, they add up to barely 9 or 10 units.
There is a discrepancy of over 920 units of mass completely missing from the fundamental building block.
It's huge.
It's as if you weighed a bag containing 3 one-ounce marbles, and the scale told you the bag weighed 100 pounds.
That missing mass is the central mystery of quantum chromodynamics. If the parts don't weigh anything, where is the substance coming from?
And this brings us to a paradigm-shifting concept championed by theoretical physicists like Frank Wilczek.
Mass without mass.
Right. He explicitly refers to this phenomenon as mass without mass. To understand it, we have to leverage Einstein's profound realization regarding energy and mass equivalence.
Without reciting the specific equation, of course.
Of course. The grand insight is that mass is not an independent property of nature. Mass is simply a measurement of the total energy content sitting inside a localized, confined system.
The locked box scenario.
Exactly. Imagine you have a completely indestructible, sealed box. Inside that box, you trap a swarm of incredibly bouncy, perfectly elastic balls that are flying around, ricocheting off the walls at lightning speed.
Okay.
Even if those balls were hypothetically weightless, the sheer kinetic energy of all that internal movement trapped inside the box would make the box itself harder to push across the floor.
It would resist your applied force.
And in physics, the resistance to being accelerated is inertia. Inertia is the very definition of mass.
That analogy cuts straight to the heart of the physics. The mass of the proton isn't derived from heavy physical bricks. It is derived from frantic, trapped energy.
It's just buzzing around inside.
The research points out that the valence quarks inside the proton are moving at relativistic speeds, a significant fraction of the speed of light. That represents a tremendous reservoir of kinetic energy.
And on top of the quarks, you have the field energy of the gluons.
The gluons being the aptly named force-carrying particles that mediate the strong nuclear force.
They are the bouncers keeping the quarks trapped in the club.
That's a great way to look at it. And their interactions carry immense energetic weight. So to truly understand where your physical weight comes from, researchers had to find a way to audit the energy inside that femtometer-sized box.
They had to break down exactly what kind of energy is trapped in the proton.
And this is remarkably difficult because the math of the strong force is notoriously intractable at low energies.
I was reading up on the methodology here, and it's a brilliant workaround for an otherwise impossible mathematical roadblock.
It really is.
In electromagnetism, physicists use a technique called perturbation theory, which works because the electromagnetic force gets weaker the further apart things are. You can approximate the math.
But the strong force doesn't work like that.
Oh. The equations for how quarks and gluons interact are so highly coupled and nonlinear that you can't just solve them analytically on a chalkboard. So physicists developed a computational method called lattice QCD.
Lattice QCD is a triumph of modern theoretical physics and supercomputing. Since continuous spacetime creates infinities in the strong force equations that we can't resolve, researchers realized they could discretize spacetime.
They chop the continuum up.
Exactly. Into a four-dimensional digital grid, a literal lattice. They place the quarks on the intersection nodes of this grid, and the gluons live on the links connecting the nodes.
It's basically rendering the quantum vacuum like a highly pixelated video game so the supercomputers can actually process the math.
That's pretty much what it is. And the computational power required for this is staggering. We are talking about the world's most powerful supercomputers running massive simulations for months just to resolve the internal dynamics of a single proton.
And when they finally run those massive simulations to audit the proton, the research reveals that the mass is divided into 5 distinct, deeply fascinating components.
We already mentioned the first one, which is the quark current masses. That's the bare mass generated by the Higgs mechanism. As we noted, it comes in at roughly 1%.
The trivial cover charge. So what makes up the rest of the pie chart?
The second component is quark kinetic energy. This accounts for the sheer relativistic speed of those 3 quarks buzzing around inside the confined space of the proton.
And how much of the mass is that?
That kinetic energy alone accounts for about 32% of your mass.
32%.
Yeah.
So nearly a third of my physical body weight is quite literally just the speed of tiny particles zooming around in microscopic circles. The momentum itself is translating into gravity-resisting mass.
Exactly. Now, the third component is gluon kinetic energy. It's crucial to understand that gluons are entirely massless particles. They have no resting mass whatsoever.
None.
Yet they are not static glue. They are highly dynamic force carriers zooming between the quarks, constantly being emitted and absorbed to keep the system bound together.
And their kinetic energy accounts for another 37% of the proton's mass.
Right.
Okay, let's pause and appreciate the absurdity of this. We have 1% bare mass, 32% zooming quarks, and 37% zooming massless gluons.
We've accounted for 70% of the proton.
And the vast majority of it is just the velocity of things that weigh practically nothing.
The remaining 30% pushes us into even stranger territory.
Oh boy.
About 9% of the proton's mass comes from something physicists call the quark condensate.
What exactly is that?
This is the energy derived from a sea of virtual particles, specifically quark and antiquark pairs, that are constantly spontaneously popping into and out of existence inside the proton.
The quantum vacuum. The idea that empty space is never truly empty. It is just teeming with potential energy waiting to manifest.
The rules of quantum mechanics dictate that you can borrow energy from the vacuum as long as you pay it back quickly enough.
Right.
These virtual particles borrow energy, manifest in the physical universe for a microscopic fraction of a second, and then annihilate each other. But inside the proton, their constant roiling presence fundamentally alters the energy landscape.
It's an ongoing background static of creation and destruction.
And that background static contributes about 9% to the proton's overall mass.
That is wild. The ghost dancer's constantly flooding the dance floor, but we are still missing a final chunk. What about the last 23%?
That is perhaps the most profound piece of the entire mass puzzle. It's called the trace anomaly.
The trace anomaly. We're going to dive deep into that later.
We will, because it requires its own dedicated analysis. But to frame it now, it essentially represents the energy of the vacuum of space itself boiling and interacting with the gluon field in a way that breaks a fundamental symmetry.
It is the quantum vacuum violently refusing to be scaleless.
Exactly.
So, synthesizing this lattice QCD audit, being a solid human being just means you are an aggregate of trillions of tiny, inescapable nightclubs.
I love the nightclub analogy.
Inside each nightclub, you've got 3 hyperactive dancers, the valence quarks moving at relativistic speeds. You've got bouncers, the gluons sprinting between them at the speed of light to keep them contained.
And the ghost dancers.
Right, you've got a continuous sea of ghost dancers popping in and out of existence on the floor. And the music is so loud, the energy is so dense that it literally boils the empty space in the room.
And none of these individual elements weigh much of anything on their own.
Most are entirely massless. But because they are perpetually trapped in that tiny club and cannot dissipate, the sheer localized chaos of the party resists being moved.
When you step on the bathroom scale, gravity is just measuring how hard it is to pull those chaotic, self-contained energy storms downward.
It is a radically different way to picture your own biology.
But mathematically, that is exactly what the rigorous supercomputer simulations are telling us.
Yeah.
You are not made of solid stuff. You are made of trapped activity.
Which naturally begs the most interesting question of all. How does the universe know how to build these nightclubs?
The architecture.
Yes. How does it trap all this chaotic energy so perfectly and so reliably across the entire cosmos? That brings up the architecture of the strong nuclear force itself. We're very familiar with gravity, and we're familiar with electromagnetism, which operates on positive and negative electrical charges.
Right.
But the strong force doesn't care at all about positive and negative, does it?
Not in the slightest. The strong force operates on an entirely different, incredibly complex property, which physicists whimsically named color charge.
Now, for anyone listening who might be newer to chromodynamics, it is vital to emphasize that this has absolutely nothing to do with visual colors.
Quarks do not possess a microscopic pigment. They are not actually red, green, or blue.
It's just a naming convention. Physicists needed a way to describe a force that operates on three distinct types of charge, rather than just the two we see in electromagnetism.
And since the mathematical rules of how these three charges mix perfectly mimic how the primary colors of light mix, they just borrowed the terminology.
Precisely. If you mix red, green, and blue light together in equal measure, you get white light. It appears colorless.
And that brings us to the most unyielding rule in the cosmic recipe book, the rule of three.
The dress code.
The literature makes it explicitly clear that for energy to be perpetually sustained in a mass form like our highly stable proton, the resulting composite particle must be perfectly colorless.
It must be what is known mathematically as a color singlet.
Exactly.
So the bouncers at the door of this Proton nightclub enforce an absolute, non-negotiable dress code. You can only enter and form a stable system if you bring a perfectly colorless group.
You need exactly one red quark, one green quark, and one blue quark.
If you show up with two reds and a green, the universe rejects you. You are unstable.
That requirement for color neutrality isn't arbitrary. It is governed by a highly specific mathematical blueprint. The research refers to it as the geometry of reality.
The geometry of reality.
Specifically, it is governed by a continuous symmetry group known as SU3, the special unitary group of degree 3.
Let's unpack the logic of SU3 without diving into the matrix calculus. Gauge symmetry can sound intimidating, but conceptually, it is essentially the underlying mathematical rulebook for how these color charges are allowed to interact and swap places, right?
That's an excellent way to conceptualize it. Imagine an incredibly fast, complex dance inside the proton where the quarks are constantly changing their colors.
Changing colors, okay.
A red quark emits a gluon and tosses it to a green quark. In the process, the red quark transitions to green, and the green quark absorbs the gluon and transitions to red.
They swap.
The SU3 gauge symmetry is the geometric blueprint that dictates every single valid move in this dance, ensuring that no matter how frantically the colors swap, the overall macroscopic state of the proton remains perfectly colorless at all times.
And because there are three fundamental colors, red, green, and blue, this geometry mathematically dictates the exact number of gluons required to facilitate all these color swaps.
Yes. The mathematics of a 3x3 symmetry system dictates that there must be exactly 8 force-carrying particles, 8 distinct gluons.
Okay.
These are the 8 unique combinations of a color and an anticolor that can be exchanged between the quarks to keep the strong force operating and the symmetry unbroken.
Wait, let's look at the basic arithmetic of that for a second. If you have 3 primary colors, red, green, blue, and 3 corresponding anticolors, anti-red, anti-green, anti-blue, shouldn't there be 9 possible combinations?
That's the logical assumption, yes.
You would pair red with anti-red, with an anti-green, red with anti-blue, and repeat for the others. 3 multiplied by 3 is 9. So why does SU3 only allow for 8 gluons? Where is the 9th gluon hiding?
This is one of the most profound reality-saving quarks highlighted in the research. The math does indeed generate 9 possible pairings. 8 of them form what is called an octet.
The octet.
These are the gluons that carry a net color charge and actively participate in the color-swapping dance. But the 9th combination is different. It forms a singlet state.
A singlet.
Mathematically, this 9th state would be a perfect, symmetrical, equal mix of red anti-red, blue anti-blue, and green anti-green.
Which means, if it's a perfect mix of all the colors and anticolors, it would be totally color neutral, all on its own. It would be a white gluon.
And remember the fundamental rule of the strong force. It only interacts with things that possess a net color charge. If this 9th color-neutral gluon actually existed in nature, it wouldn't feel the strong force. It wouldn't be bound by the rules of the nightclub. It wouldn't participate in confinement.
If it isn't bound by confinement, what would it actually do? Where would it go?
It would leak out of the proton entirely. Because it has no net color charge, the strong force couldn't trap it. It would radiate outward, flying through the vacuum of space, much like a photon of light does for the electromagnetic force.
Okay.
But unlike a photon, which only interacts with electrically charged particles, this unconfined gluon would carry the strong nuclear force over massive macroscopic distances.
Oh, that sounds catastrophic.
It would be the immediate end of reality as we know it.
Wow.
The strong force is exponentially more powerful than gravity or electromagnetism. If a long-range strong force existed via this ninth gluon, it would cause all the ordinary colorless atoms in the universe, the carbon in your cells, the oxygen in the air, the iron in the Earth's core, to violently interact with each other at a distance.
This is a universal crunch.
Macroscopic matter would simply collapse under the overwhelming attraction. Planets, human beings, biological chemistry, none of it would be possible. The universe would instantly crush itself into a chaotic, ultra-dense soup of violently interacting subatomic sludge.
So, to save reality from immediate collapse, the universe basically audited its own math, realized the ninth combination would destroy all macroscopic life, and implemented a strict geometric exclusion.
Exactly.
It demands a traceless matrix. Every single gluon that exists must carry a net color charge. No colorless gluons are allowed to manifest. You must be locked up or you cannot exist.
The elegance of the SU3 blueprint is that the mathematics inherently require the generator matrix of these interactions to be traceless, which permanently and naturally excludes that highly destructive neutral ninth state.
The universe utilizes an exclusive 8-part code to ensure every ounce of energy related to the strong force stays completely confined within the boundaries of the proton.
Knowing the mathematical rule is one thing, but how does the universe actually enforce this confinement physically?
Right. How does it keep this hyperactive light-speed energy from just overwhelming the boundaries and blowing the proton apart?
The perpetually sustainable nature of mass depends on two deeply counterintuitive properties of quantum chromodynamics. The first is a phenomenon known as asymptotic freedom.
Asymptotic freedom.
This was a monumental theoretical discovery in the early 1970s by physicists Frank Wilczek, David Gross, and H. David Pulitzer, work that eventually earned them the Nobel Prize.
It sounds like an oxymoron when we are talking about the most confined space in the universe. What exactly is the inner freedom of a proton?
Normally, human intuition tells us that a force gets stronger the closer two interacting objects get. If you bring two powerful neodymium magnets close together, the attractive force skyrockets and they snap together violently.
Or if you step closer to a fire, the radiant heat intensifies.
Right. But the strong force, when observed deep inside the proton, does the exact opposite. As the distance between two quarks approaches zero as they get incredibly close to each other, the strong force between them effectively vanishes. It gets weaker.
That is completely backward to how classical physics operates. So when the quarks are packed tightly in the absolute center of the proton, they don't even feel the pull of the gluons.
They behave almost as if they are completely free, uninteracting particles. They zip around at relativistic speeds, totally unbothered by each other's presence, provided they stay very close together.
It's like being trapped in an incredibly tiny escape room. As long as you stay right in the exact center of the room, you can dance around completely free, throwing your arms in the air, totally unrestricted by the walls. You wouldn't even know you were trapped.
A very apt visualization. But the flip side of asymptotic freedom is the second, much more rigid property. Confinement.
The walls of the room.
What happens when the quark stops dancing in the center and attempts to leave the room?
The perpetual lock engages.
Precisely. As the quarks attempt to move apart, the strong force between them doesn't fade away or dilute like gravity or light does. It gets exponentially stronger.
Because with light, the photons spread out over a wider area the further they travel. The beam gets dimmer, but the strong force doesn't spread out.
It doesn't spread out because of a unique characteristic of gluons. Unlike photons, which have no electrical charge and therefore ignore each other, gluons themselves carry color charge.
Meaning they interact with each other.
Yes. This constant self-interaction causes the color field lines between the separating quarks to tightly compress into narrow, highly dense bundles. The literature commonly refers to these compressed field lines as flux tubes or chromodynamic strings.
The ultimate subatomic rubber band. As the quark moves toward the edge of the proton's boundary, the flux tube stretches, and the tension pulls back harder and harder. Let's play out a thought experiment here.
Okay.
What if I had a pair of infinitely strong microscopic tweezers? What if I grabbed one of those red quarks and I pulled with all the mechanical strength in the universe? I just keep pulling, stretching that flux tube further and further. Does the quark eventually pop out of the proton?
If you attempt that, you will trigger a violent quantum event known as hadronization, or, to use a more visceral term, the snap.
The snap.
As you use your tweezers to pull that quark away, the energy stored inside that stretching flux tube increases linearly. To give you a sense of scale, the energy density of a stretched flux tube is roughly 1 gigaelectron volt per femtometer.
Which means what in our world?
In macroscopic terms, that tiny subatomic string is exerting about 10 tons of pulling force.
10 tons of force between two microscopic particles that weigh almost nothing. That is terrifying.
You are pumping immense, unimaginable amounts of energy into the system just to stretch that strong force string. Eventually, the energy contained within that stretched flux tube becomes so immense that it crosses a critical threshold.
It breaks.
The universe steps in to resolve the massive tension. The string literally snaps.
But the snap doesn't just break the bond and leave you holding a single isolated quark in your tweezers, does it?
Never. The universe absolutely forbids the existence of an isolated color charge. When the flux tube snaps, all that immense mechanical energy you pumped into stretching it is instantaneously converted into mass, dictated directly by Einstein's equivalence principle.
It makes a new particle.
Out of thin air, fueled purely by the energy of the snap, the universe summons a brand new quark-antiquark pair.
So the timeline of events goes like this. I try to pull a red quark out of the proton, stretching this 10-ton rubber band of energy. The tension peaks, the rubber band snaps, and boom, the pure energy of the snap creates a brand new anti-red quark right next to the one in my tweezers, instantly pairing with it to form a new color-neutral particle called a meson.
Yes.
And simultaneously, back inside the original proton, a new red quark manifests out of the remaining energy to take the place of the one I removed, leaving the original proton perfectly intact and colorless.
That is exactly the sequence. No matter how much energy you apply, no matter how hard you try, you can never isolate a single quark.
It's impossible.
You simply end up creating more trapped, colorless particles out of the energy you expend. This hadronization mechanism is the perpetual lock. It guarantees that all this immense hyperactive energy remains permanently trapped within a tiny radius about 0.84 femtometers.
When you lay it out like that, it fundamentally changes how I visualize the Big Bang.
It should.
We are always taught to picture the Big Bang as this singular outward explosion of pure, boundless, uncontained energy. But if it weren't for this femtometer lock, if it weren't for these flux tubes, that initial energy would have simply dissipated out into the cold, expanding void.
It would have gotten thinner and thinner until the universe was just a tepid, empty soup.
Instead, the universe utilized these unbreakable rubber bands to literally grab chunks of that roaring, primordial Big Bang energy and freeze it in place. It compartmentalized the explosion into trillions of tiny, permanent, self-sustaining spheres.
It is a staggering realization. The raw energy of the cosmic dawn wasn't lost to expansion. It was arrested. It was mathematically frozen into the stable matter we see today by the unbreakable rules of confinement.
Okay, so we understand the rule. SU3 symmetry, exactly 8 gluons, perfect confinement via flux tubes. But this leads to a question that borders on philosophy, one that is heavily debated in theoretical physics.
The why question.
Why? Why does the universe utilize this specific blueprint? Why the rule of exactly 8? Who or what wrote that geometric rulebook? To explore this, we have to look at the intersection of fundamental physics and pure abstract mathematics.
We have to talk about the octonions.
We are definitely venturing into the deepest, most mind-bending strata of theoretical research now.
We are moving beyond observing physical phenomena and attempting to understand the underlying mathematical skeleton of reality itself. To comprehend why the universe relies on an 8-part blueprint for the strong force, we have to examine a mathematical concept called the normed division algebras.
Let's walk through the logic of this carefully. What exactly is a division algebra, and why does the universe care about it?
At its most basic level, a division algebra is a number system where you can reliably perform the 4 fundamental arithmetic operations addition, subtraction, multiplication, and division without breaking the rules of math.
Meaning, you can always divide by any non-zero number and find a single, definitive, unambiguous answer.
Now, common sense might suggest you could do that with any set of numbers. But mathematically, as you try to expand number systems into higher and higher spatial dimensions, the fundamental rules of arithmetic begin to break down.
They fail.
You lose commutativity, you lose associativity. The math stops working.
Right. So of all the infinite possibilities in mathematics, how many of these perfectly stable number systems actually exist?
In all of mathematics, there are only 4 normed division algebras. It is an incredibly exclusive, finite club.
And the research links these 4 specific math systems directly to the physical forces of our universe. Let's start from the bottom, dimension 1.
The first system is the real numbers. This is the standard arithmetic you learn in grade school. It operates in one dimension, just points sitting on a straight, infinite line.
And in physics?
In physics, real numbers map perfectly to the mechanics of the classical world. They're used to describe simple, one-dimensional scalars like a point in time, or the classical macroscopic idea of mass.
Simple, straightforward, intuitive. What happens when we move up a dimension?
The second system is the complex numbers. This system introduces the concept of imaginary numbers, specifically the square root of -1. Complex numbers operate in 2 dimensions, a flat 2D plane.
And what force does that map to?
When we look at physics, complex numbers provide the exact, necessary mathematical framework to describe electromagnetism. The equations that govern the behavior of photons, light, and radio waves are inherently tied to this 2D math.
So a 2-dimensional mathematical concept governs the force of light. Fascinating. Let's keep climbing the dimensional ladder.
The third stable system is the quaternions. These operate in 4 dimensions. They were discovered by William Rowan Hamilton in the 19th century.
And they are notoriously difficult to work with.
Very difficult, because the order in which you multiply them changes the answer. But remarkably, the 4D mathematics of quaternions aligns perfectly with the physics of the weak nuclear interaction.
The force responsible for radioactive decay and nuclear fusion in the sun. Okay, the pattern is striking. 1D maps to classical physics, 2D maps to electromagnetism, 4D maps to the weak nuclear force. What is the fourth and final stable number system?
The octonions. These operate in 8 dimensions. They are the largest, most complex, and undeniably the weirdest of the 4 division algebras.
8 dimensions.
When calculating with octonions, you not only lose the ability to swap the order of multiplication, but the grouping of the numbers changes the outcome entirely. They are deeply non-associative. But what makes them the subject of intense focus in modern theoretical physics is their inescapable connection to the strong nuclear force.
The 8-dimensional math system governs the strong nuclear force, the 8 gluons.
The parallels are too precise to be a coincidence. The literature highlights the ongoing work of pioneering mathematical physicists like Cole Fury and John Baez. They study what is known as the automorphism of nature.
That sounds poetic.
It is. They investigate the inherent symmetry groups that naturally arise within these hypercomplex number systems. The octonions possess a very unique, overarching symmetry structure, a shape known in mathematics as G2.
I am trying to imagine a perfectly symmetrical geometric shape, but one that exists simultaneously in 8 dimensions, and my brain is just refusing to render it.
It's entirely impossible for the human brain to visualize, as we evolved to understand 3 spatial dimensions. But we don't need to visualize it to understand the mathematical logic. Here is the monumental breakthrough researchers have focused on.
Lay it on us.
If you take that highly complex 8-dimensional G2 symmetry and you mathematically lock down just one of its imaginary units, essentially anchoring a single part of this hyperdimensional structure in place, the symmetry that remains, the geometric shape that is left over, is exactly SU3.
Wait. The SU3 symmetry, the exact geometric blueprint that dictates the strong force, the color charges, and the 8 gluons, is literally just the mathematical shadow of an 8-dimensional number system.
Yes. The SU3 symmetry isn't just a random, arbitrary rule the physical universe made up to trap energy. It is the internal, inescapable geometry of the octonions.
That is mind-blowing.
The research heavily suggests that the underlying knowledge of physical creation, the reason there are 3 color charges and exactly 8 gluons, is deeply, irrevocably embedded in this abstract pure math.
The universe utilizes the 8-dimensional structure of the octonions to provide the exact 8 hooks, or force carriers, necessary to bind the 3-colored quarks into a perpetually stable mass form.
Exactly.
It's as if the universe didn't even have to invent the strong nuclear force from scratch. It just logged into a cosmic platonic app store, downloaded the only 8-dimensional geometry application that compiles without crashing, and let it run reality.
And the output of that geometric code is protons, chemistry, stars, and ultimately human observers.
That is a remarkably accurate way of summarizing the theoretical physics at play. It suggests that mathematics strictly precedes physical reality.
The structure of the quantum vacuum, the very rules of confinement, are dictated by the rigid constraints of these hypercomplex numbers. Reality is just the physical manifestation of math.
Which perfectly sets up the next critical piece of the puzzle. If the vacuum of space is governed by eight-dimensional math, how does that empty vacuum actively generate the physical weight we feel? Let's talk about the trace anomaly.
This is a highly technical, yet absolutely critical part of the mass creation recipe. If you recall our lattice QCD audit of the proton earlier, we established that roughly 23% of the proton's mass is derived from this mysterious trace anomaly.
Right, and you teased this earlier as the boiling vacuum. Explain to me the mechanics of how the empty vacuum of space can physically weigh anything, let alone account for nearly a quarter of my body weight.
To understand the trace anomaly, we first need to understand a principle called scale invariance.
Scale invariance.
In classical physics, if you have a theoretical framework composed entirely of massless particles like the quarks before they interact with the Higgs field, and the gluons, which are permanently massless, the equations shouldn't care how zoomed in or zoomed out you are.
Because there's no inherent mass to set a size.
Right. The physical laws should look exactly the same, whether you are examining a space the size of a subatomic particle or a space the size of a galaxy.
It's like looking at a perfect mathematical fractal. No matter how deep you zoom into the Mandelbrot set, you see the same patterns repeating endlessly. It has no fixed inherent size.
Precisely. If the strong nuclear force were perfectly scale invariant, the proton could theoretically be the size of a grain of sand, or the size of a football, or the size of Jupiter. It would have no fixed physical scale.
And because mass and confined energy are inextricably linked, it would have no fixed mass.
Exactly. But obviously that isn't the reality we observe. Protons do have a fiercely guarded identical size. Every single proton in the universe is exactly 0.84 femtometers in radius.
So something fundamental must be breaking that fractal-like zooming. Something is breaking the scale invariance.
What forces the zoom to stop? What breaks it?
That's the question.
The relentless, chaotic nature of quantum mechanics. Specifically, the reality that the vacuum of space is never truly empty. We talked about virtual particles spontaneously popping in and out of existence.
The ghost dancers.
The gluon field inside the proton isn't just interacting with the quarks. It is constantly, violently interacting with the quantum vacuum itself. The vacuum is boiling with these quantum fluctuations.
So the bouncers in our nightclub aren't just wrestling with the three dancers. They are constantly tripping over the spectral ghosts that are bursting out of the floorboards every millisecond.
And that continuous interaction between the dynamic gluon field and the boiling quantum vacuum generates a dense, inherent energy. In quantum field theory, this process is known as quantum renormalization.
How does that work?
The coupling constant of the strong force runs. It changes depending on the energy scale of the interaction. This completely shatters the perfect symmetry of scale invariance. The universe undergoes a process called dimensional transmutation.
Form a mutation.
It forces the system to generate a hard physical scale out of dimensionless parameters. It stops the infinite fractal zooming and definitively states, no, the boundary of the particle is exactly here.
And the sheer energy required to set that definitive boundary, to fight back against the boiling vacuum and draw a solid, unyielding line in the sand, physically manifests as mass.
Yes, that energy anomaly, the cost of breaking scale invariance, accounts for roughly 23% of the proton's mass.
So what does this actually mean for you, the person listening right now? If you step on a scale and you weigh 150 pounds, roughly 34 pounds of your physical body weight is literally nothing but the invisible quantum vacuum of empty space.
Continuously boiling and bubbling.
And being locked down into a fixed size by eight-dimensional geometric rules, you are constructed of abstract math and boiling emptiness.
It forces us to completely reevaluate the classical definition of substance. The research emphasizes that this is the ultimate act of cosmic creation. The vacuum itself develops an inherent energy density through the breaking of these mathematical symmetries, and our macroscopic bodies experience that dense vacuum energy as physical touch, as solidity, as weight.
But if we are just aggregates of trapped, boiling, hyperactive energy desperately trying to push outward, how are we so incredibly stable?
That's the billion-dollar question.
Why don't I just evaporate or spontaneously explode? The Big Bang energy is trying to get out. The vacuum is boiling. Why does the proton hold together so perfectly? Let's dive into the mechanics of proton stability. Let's explore the eternal vault.
A central focus of this research is understanding why this specific chromodynamic recipe creates a perpetually sustainable mass form. And the proton is the undisputed champion of sustainability in the Standard Model.
As far as our current observational physics can determine, an isolated proton is, for all practical intents and purposes, entirely eternal.
Eternal is a strong word in physics.
Just how long is eternal?
To test this, physicists built massive underground detectors, like the Super Kamiokande in Japan, filled with thousands of tons of ultra-pure water, just waiting to see if a single proton would spontaneously decay.
And have they seen it?
They haven't seen it happen. Based on these experiments, the current lower bound on the half-life of a proton exceeds 10 to the 34th power years. That is a 1 followed by 34 zeros.
To put that time scale in perspective, our entire universe, since the Big Bang, is only about 13 billion years old. Protons will easily outlive the stars, the galaxies, and possibly the universe itself.
So why? What is the specific mechanism that makes this arrangement of 3 quarks and 8 gluons so unbelievably invincible?
It comes down to a fundamental conservation law in quantum accounting known as baryon number conservation.
Think of it as an ironclad cosmic law that dictates the total number of heavy particles, baryons in a closed system, must remain constant unless acted upon by unimaginably extreme universe-breaking forces.
Now remember, our rule of 3 in the SU3 geometry from earlier. To exist as a stable state, a particle must be color neutral, containing exactly all 3 colors.
Right. You have to meet the exact dress code to stay in the club.
Within the constraints of the SU3 framework, the proton is the absolute lightest possible combination of 3 quarks that achieves that necessary color-neutral state.
In physics terms, it sits at the absolute bottom of the potential energy well. For any particle to decay, it must transform into a configuration of lighter particles in order to shed energy.
But for the proton, there are no lighter color-neutral combinations of 3 quarks in existence.
So it's standing at the absolute bottom of a deep crater. Gravity, or in this case quantum decay, wants to pull it lower, but it can't fall any further. It literally has nowhere to go.
It cannot decay because there is no lower energy state for it to transition into without violating the sacred rule of color neutrality.
Exactly. The SU3 symmetry acts as an impenetrable vault. Because the proton is the ultimate ground state of this color geometry, the immense energy trapped inside cannot leak out or decay. It is preserved perfectly across cosmic timescales.
But importantly, not all subatomic particles are so lucky. Let's contrast this eternal, majestic proton with its incredibly tragic sibling, the poor, doomed neutron.
The neutron provides a perfect counterexample. It is the other major nucleon found inside the nucleus of an atom. But it utilizes a slightly different recipe. Instead of 2 up quarks and 1 down quark, the neutron is composed of 1 up quark and 2 down quarks.
It still possesses exactly 3 quarks, so it still successfully meets the color-neutral dress code.
It does. It is a valid color-neutral baryon. But here is the critical distinction. The bare mass of a down quark, as provided by the Higgs field, is ever so slightly heavier than the bare mass of an up quark. Because the neutron contains 2 of these heavier down quarks, the neutron as a whole composite particle is slightly heavier than the proton. On the subatomic measurement scale, the proton weighs roughly 938.2 mega-electron volts.
And the neutron?
The neutron weighs about 939.5 mega-electron volts.
We are talking about an incredibly tiny mass difference. It's a fraction of a % of difference in weight.
Yes, but in the ruthless economy of the quantum world, that fractional difference is the difference between eternal existence and rapid death. Because the neutron is slightly heavier, it is no longer resting at the very bottom of the energy well. It is perched slightly up the slope of the crater.
Oh, so it can fall.
Exactly. When a neutron is left alone, isolated in the vacuum of space outside the protective nucleus of an atom, it is inherently unstable. The laws of thermodynamics dictate that it desperately wants to reach the lowest possible energy state.
So, facilitated by the weak nuclear force, remember our 4D quaternion math from earlier, one of the neutron's down quarks will spontaneously undergo beta decay. It transforms into a lighter up quark.
In the process, it spits out an electron and an antineutrino to conserve charge and momentum, and it officially turns into a proton.
It tumbles down the hill and settles at the bottom as a stable proton. How fast does this catastrophic decay happen? If I hypothetically held an isolated neutron in my hand, how long before it transforms?
An isolated neutron has a mean lifespan of roughly 15 minutes, about 880 seconds. Then, poof, it decays.
15 minutes. The proton survives for 10 to the 34th years, and its almost identical twin can't even last through a sitcom episode. That is structurally tragic. But wait, if isolated neutrons decay in 15 minutes, how are there any left in the universe? My body, the Earth, the sun, we are all packed full of neutrons, right?
The neutrons in your body survive exclusively because they are not isolated. When neutrons bind tightly together with protons inside the dense nucleus of an atom, the complex energy dynamics and binding energies between them essentially prop the neutron up. They lean on each other. The nuclear environment modifies the energy landscape, preventing the neutron from tumbling down the hill. But the moment you isolate them, they don't last.
This highlights something incredibly profound about the architecture of our universe. Let's look closely at that tiny mass difference one more time. Proton at 938.2, neutron at 939.5.
The literature repeatedly emphasizes that this highly specific ratio, the fact that the proton is the lighter of the two particles, is the golden ratio for biological life.
It is the absolute prerequisite for our existence. It touches on the anthropic principle. Imagine for a moment a universe where the bare masses of the up and down quarks were slightly tweaked by the Higgs field, making the proton the heavier particle. What would happen?
The proton would be the one perched on the side of the hill.
Yes. The proton would be inherently unstable, and it would spontaneously decay into the neutron to reach the lower energy state.
If protons decayed, hydrogen couldn't exist. A hydrogen atom is literally just a single isolated proton with an electron orbiting it.
Exactly. If the proton were heavier, the vast clouds of primordial hydrogen created in the aftermath of the Big Bang would have simply evaporated into neutrons within 15 minutes.
Without hydrogen gas, stars cannot ignite. Without the nuclear fusion inside stars, there is no mechanism to forge carbon or oxygen or iron. There is no water. There are no planets. There is absolutely no biology.
The universe would just be a dark, cold, featureless void filled with drifting, lifeless neutrons and radiation. The realization that the universe locked in this exact fractional mass ratio, the proton winning the race to the bottom of the energy by just 1.3 mega electron volts, is quite literally the only reason we are sitting here having this conversation today.
It is a profoundly humbling realization. The eternal stability of the proton ensures that the kinetic energy of the early universe remains securely locked up and accessible to form complex chemistry, molecules, and eventually conscious observers across billions of years of cosmic history.
Which brings us to the ultimate synthesis of all these mind-bending concepts. This is the grand finale of the mass creation story, or as I like to call it, the harmonic compromise.
Over the course of this deep dive, we have entirely dismantled the classical idea that mass is a static, solid substance. We have seen that it is a highly dynamic process governed by eight-dimensional geometric blueprints, unbreakable confinement strings, and the boiling quantum vacuum.
And we playfully roasted the Higgs boson at the beginning, so it's only fair we circle back to it one last time. We established that the Higgs field acts like cosmic molasses, imparting just a tiny 1% bare mass to the quarks.
Right. And as we noted, if you deactivated the Higgs field, protons would still exist, and they would still retain roughly 90% of their mass. The universe would undoubtedly look different, the size of atoms would change, chemistry would be heavily altered, but solid, heavy matter would absolutely still exist. Mass is fundamentally a chromodynamic creation, an emergent property of energy, not strictly a Higgs creation.
So if the mass of the proton, the crucial 938 mega-electron volt value that allows hydrogen, stars, and life to exist, isn't arbitrarily dictated by the Higgs field, what exactly determines that specific number? Why does the energy settle at 938? Why not 500 or 1,000,000? Frank Wilczek proposes a beautiful, elegant explanation for this in the literature. He calls it a stable compromise.
Yes, Wilczek synthesizes the emergent creation of mass as an epic, microscopic tug-of-war between two titanic fundamental quantum forces. It is the ultimate balancing act in nature. Let's look at force number one.
The strong nuclear pole of the gluons.
The bouncers. We know they enforce confinement, but what is their ultimate mathematical goal?
Because of the property of anti-screening and the self-interacting nature of the flux tubes, the gluons want to perfectly, efficiently cancel out the color charges of the quarks. The most mathematically efficient way to achieve perfect color neutrality is to pull the red, green, and blue quarks exactly on top of each other.
The gluons want to compress the quarks into a single, infinitesimal, zero-dimensional mathematical point where all colors perfectly neutralize.
So the strong force is actively trying to collapse the proton down to a physical size of absolute zero.
That is its thermodynamic goal, yes.
But obviously, protons are not infinitely small. They have a measured radius of 0.84 femtometers. So something incredibly powerful must be pushing back against the 10-ton pull of the flux tubes. What is force number 2?
Force number 2 is one of the most famous unyielding rules in quantum mechanics, the Heisenberg uncertainty principle.
Let's unpack Heisenberg, because it's often misunderstood. Usually when people hear Heisenberg uncertainty, they assume it just means our microscopes aren't good enough to measure tiny things without bumping them. It's treated as an observer effect. But that's not the fundamental truth, is it?
Not at all. It is not a limitation of our human technology. It is a fundamental limit built into the very fabric of the universe. The Heisenberg uncertainty principle dictates the relationship between position and momentum. It states that you cannot simultaneously define both the exact physical position and the exact momentum of a quantum particle.
And this mathematical law has a severe physical consequence. If you try to force a particle into a tiny, rigorously exact location, if you try to pinpoint its position perfectly, its momentum becomes completely chaotic. It spikes dramatically.
So if I trap a quark in an impossibly tiny box, restricting its position, it responds by vibrating with unimaginable violence, pushing against the walls to break out.
Exactly. The tighter you squeeze the box, the higher the kinetic energy of the trapped particle becomes. So let's look at Wilczek's tug of war. The gluons are pulling the quarks inward, attempting to crush them into a perfect dimensionless point.
But as the quarks are forced closer and closer together, their position in space becomes more strictly defined. The Heisenberg uncertainty principle instantly kicks in, and the quark's kinetic energy goes through the roof. They push outward with immense, frantic quantum momentum.
It's the classic unstoppable force meeting an immovable object. The gluons squeeze inward, the Heisenberg uncertainty pushes back outward, and the harder the gluons squeeze, the harder the quantum pressure pushes back.
And eventually, these two titanic forces reach a perfect stalemate. They reach a point of absolute equilibrium where the inward pull of the chromodynamic flux tubes exactly matches the outward kinetic resistance of the quantum uncertainty.
And what happens at that exact point of equilibrium?
The proton stops shrinking. It stabilizes. It achieves its fixed permanent radius of 0.84 femtometers. And if you run the math, if you measure the total trapped energy of that perfect stalemated system, the energy equates to exactly 938 subatomic mass units.
That is awe-inspiring. So the mass of the proton isn't an arbitrary parameter dialed in by a creator. It is the literal physical measurement of the stalemate between two foundational rules of the universe fighting each other to a standstill.
It is what the theoretical literature poetically refers to as a resonant frequency, a music of the void. Think of the mechanics of a guitar string. When you pluck it, it naturally vibrates at a highly specific frequency based on the tension of the string and the physical length of the fretboard. The mass of the proton is the resonant frequency of the gluon field when it strikes a chord with quantum uncertainty.
And the implications of that are staggering. If the underlying geometry of the universe were altered even slightly, if there were 9 gluons instead of 8, if the mathematics was 4-dimensional instead of 8-dimensional, if the strong force didn't grow exponentially stronger with distance, this cosmic chord would be entirely out of tune. The compromise would fail.
And if that harmonic compromise fails, the localized energy dissipates, and solid matter simply vanishes from the universe. The mass of the universe, the weight of your own body, is quite literally a harmonic resonance. We are constructed of cosmic music.
What an unbelievable journey this has been. Let's synthesize everything we've uncovered today. You look at your hand and your brain tells you that you see flesh, bone, solid matter. But when we dive deep into the subatomic research, we find out that you are not made of solid stuff at all. You are constructed entirely of pure massless energy, energy that is moving at a fraction of the speed of light, boiling up from the very vacuum of space itself.
And the only reason you aren't evaporating into a cloud of chaotic light radiation right now is because an 8-dimensional geometric blueprint called the strong nuclear force has thrown a perpetual lock around that energy.
It has trapped the chaos in an eternal stalemate with quantum uncertainty, creating the brilliant optical illusion of weight, solidity, and mass.
It profoundly shifts our entire paradigm of reality. It forces us to stop seeing the universe as a collection of objects and start seeing it as a collection of localized rules.
Yeah.
And it leaves us with a final provocative thought to mull over. If the solidity of everything you touch is actually just the emergent result of a geometric equation locking down motion,
Yeah.
then matter isn't a substance at all, it is an event.
An event.
Yes. Every single atom in your body, every proton in your cells, isn't a static thing that was manufactured billions of years ago in the past and left sitting around on a shelf. It is an ongoing, highly localized explosion. It is a frantic storm of massless energy that is actively being contained by mathematics at this exact fraction of a second. You are a continuously sustained event, which raises the ultimate, perhaps slightly unsettling question.
What's the question?
If matter is just a geometric knot tying up the energy of the vacuum, what happens if humanity ever figures out how to untie it?
That is a terrifying and thrilling thought. What happens if we learn to pluck that quantum guitar string ourselves? What kind of reality could we build if we understood how to directly command the 8-dimensional geometry of mass? It's definitely something for all of you to ponder the next time you step on the bathroom scale and complain about the number. Thank you for joining us on this deep dive.
I'm Satoshi.
And I'm Satoshi. Keep questioning the fundamental reality around you. And